Chapter 8, Non-Electrolyte Solutions. Section 8.2, Colligative Properties. Colligative properties of the solvent in an ideal solution depend on the quantity, but not the identity of the solute added into the solvent. Osmosis is one of the colligative properties. If we look at this diagram, in this beaker of water, we have a semi-permeable membrane that allows water molecules to pass through, but not the salt. Now if we have this beaker, we will see water moves from left to right. And you can see there's a height difference. And this height difference causes a pressure difference right here. And the pressure difference is roughly rho GH. Rho is the density of the solution, G is the gravitational acceleration, and H is the height difference. So rho GH is the pressure difference over here, between here and here. And now let's look at osmosis theoretically. Pure solvent diffusing through a membrane to dilute a solution is called osmosis. So from here to here. But why do water molecules go from left to right? It's pretty simple. The chemical potential of water depends on its mole fraction. On the left hand side we have a mole fraction of 1. On the right hand side we have a mole fraction less than 1 for water. So that means the chemical potential of water on the left is higher than the chemical potential on the right. Therefore water diffuses through until it's balanced by this height difference. And of course this height difference will generate a pressure difference. So between this level and this level there's a pressure difference, rho GH, density multiplied by gravitational acceleration multiplied by the height difference. Now we can compute osmotic pressure pi. Osmotic pressure pi is the pressure raised in a solution compared with that in the solvent. There's an equation for the calculation. The van der Waals equation of osmotic pressure is this: pi, which is osmotic pressure, times molar volume equals the mole fraction of the solute in this right hand side multiplied by RT. The chemical potential of the solvent on the right hand side of the semi-permeable membrane is this. It's mu sub I in a solution equals the chemical potential of pure I plus RT times the natural logarithm of X. You can see when the mole fraction of I decreases, its chemical potential decreases. So again, it's just on the right hand side we have the mole fraction of water less than 1, and that's why the chemical potential of water on the right hand side is less than the left hand side. Again, X is the mole fraction of the solvent. In an ideal solution, the change of the chemical potential of the solvent depends on its mole fraction, and that means the chemical potential of the solvent does not depend on the identity of the solute. So you can put any other chemical in the solvent as long as you have the same mole fraction for the solvent, you're gonna get the same amount of osmotic pressure, and of course some other colligative properties. As more solute is added, X decreases, mu decreases. Well, I'm talking about the mu of the solvent. It decreases, and X is also the mole fraction of the solvent. So that means adding solute stabilizes the solvent. Lower chemical potential means more stable. Now let's do some theoretical derivation. So again, we start from this. Okay, we have pure water on the left, we have aqueous solution on the right. And when you look at this beaker, actually the water on the left has higher chemical potential than the water on the right. So water passed through this membrane, and now we have a height difference. The pressure difference between here and here is called osmotic pressure, denoted by pi. Now let's do some derivation. The mu is simply the differential of molar Gibbs energy for a pure substance. When temperature is constant, we have d mu equals molar volume times dp. Therefore, at equilibrium, we have over here, this is the chemical potential of water on the right hand side. It's equal to the chemical potential of pure water plus RT Lnx. Why is that? Again, over here, the mole fraction x is not 1. The mole fraction x is less than 1. So you can see the sum of these two components is less than the chemical potential of pure water. However, on the right hand side, we have some additional chemical potential originates from this part. You can see d mu is molar volume times dp. Now we have additional osmotic pressure pi, so they differ by, so this pressure and this pressure differ by pi, and therefore over here the chemical potential is higher than this by molar volume times pi. So really, if you look at the chemical potential of water on the right hand side, this level, it's equal to the chemical potential of pure water over here. Alright, and we can equate these two equations, left equals right, so the chemical potential here equals the chemical potential here when just the substance is at equilibrium. And on the right, we have this correction due to the mole fraction. We have another correction due to the osmotic pressure. And since left equals right, so the sum of these two should be 0. And since the sum of these two should be 0, and we have this equation, the molar volume of this solution times pi is equal to negative RT times the natural logarithm of x. X is the mole fraction of water. And typically this x is close to 1 because we have an aqueous solution, and mostly it's water, so x is close to 1. When that's the case, we can expand Lnx into its Taylor expansion, also called Maclaurin expansion, to get this approximation. When x is close to 1, Lnx is approximately x minus 1. So really, if you have Ln 0.99, it's very close to 0.99 minus 1, which is negative 0.01. So we can easily estimate the logarithm of any number that's close to 1. So what about logarithm of 1.1? Well, roughly the value is 1.1 minus 1. So that's it. In this case, x is close to 1, x is less than 1. So we have this equation, Lnx is negative. It's approximately x minus 1, which is also negative. And x minus 1 is simply negative mole fraction of solute. It's just because the mole fraction of solute plus the mole fraction of solvent should be roughly 1. Now we can replace this Lnx with negative x of solute. We have two negative signs, they cancel. Now we get the Van Hoff equation. The molar volume of the solution times this osmotic pressure is equal to the mole fraction of the solute times R times T. It's a bit hard to memorize the equation, but we can multiply both sides by the total number of moles N on the right hand side, and then we have pi times V. And V is the total volume equals RT times, now we have N times the mole fraction of solute. This is simply the number of moles of solute. Alright, so we have this equation. Pi v is approximately equal to n solute RT. This is a bit easier to memorize due to its similarity to the ideal gas law. PV equals nRT. You just need to replace PV with pi v. Replace nRT with n of the solute and times RT, and that's it, and you get this Van Hoff equation. Of course, you can use this equation as well. Now let's look at one example problem 8.2.1. Calculate the room temperature osmotic pressure between pure water and an aqueous solution of 0.1 molar glucose. In the aqueous solution, the number of moles of water in 1 liter is approximately this much. In 1 liter, you have roughly 1,000 grams of water, and 1,000 grams of water is roughly 1,000 over 18 moles, which is roughly 55 moles. Now let's look at this equation for the osmotic pressure. The Van Hoff equation is pi v equals RT times n solute. Let's just use this equation. So pi is RT times n solute over V, and we have R, and we have T, and we have this molar volume. And now we just plug in all the numbers. 0.1 molar is 0.1 mole over liter. So, and we cancel mole and mole. Joule and L, actually they do not simply cancel. 1 joule over 1 L, I think, is 1,000 pascals. Okay, because 1 liter is 10 to the power of -3 cubic meters. So we put all the things together. We have this times 0.1, and then times 1,000 pascals. I think we'll get this many pascals, and that's 2.5 bars. The osmotic pressure between pure water and 0.1 molar glucose is 2.5 bars. Now we're going to work on a slightly different problem, 8.2.2. We're going to calculate the room temperature osmotic pressure between pure water and a aqueous solution of 0.1 molar sodium chloride. So this question looks similar to the previous question, but don't forget 0.1 molar sodium chloride decomposes into 0.2 molar of particles. You get 0.1 molar sodium plus and 0.1 molar chlorine minus. Because the decomposition is complete, each mole of sodium chloride becomes 2 moles of particles. That's why we need to multiply this by 2. And now we have actually 2 different solutes. We need to have the number of moles of both together. And in this case, the total number of moles of sodium plus and chlorine minus is 2 times that of NaCl. So when you have 0.1 molar NaCl, really you have 0.2 molar particles or 0.2 molar ions. And again, colligative properties do not depend on the identity. So whether it's sodium plus or chlorine minus, well, it's counted as 1 particle. And now we just plug in the numbers again, except over here we have 0.2 mole per liter. And then we cancel mole, and 1 joule is 1,000 pascal times a liter. We do everything, we have 5.0 bars. This osmotic pressure is 2 times this osmotic pressure, only because 1 unit of NaCl becomes 2 particles, sodium plus and Cl minus. Now let's look at 2 other colligative properties. One is boiling point elevation, the other is freezing point depression. So we have this experience. if you add antifreeze in water, you can lower the freezing point of water. You can also elevate its boiling point at the same time. And the boiling point elevation and freezing point depression take place simultaneously. They depend on the quantity of solute, but not really on its identity. Therefore, they are colligative properties. Now let's look at a chemical reaction. Now assume this enthalpy of reaction is independent of temperature. This is a reasonable assumption. You can say the enthalpy of reaction does depend on the temperature, and the dependence is the change in the CPM of the reactants and versus products. So really we look at delta CPM of the reaction. However, the integral of delta CPM dt of the reaction is usually much smaller than the enthalpy of reaction, and therefore it's reasonable to assume this is approximately independent of temperature. In that case, we can write out this equation, lnk2 minus lnk1. So we're looking at the difference between the logarithms of the equilibrium constant at temperature 2 versus temperature 1. It's equal to negative enthalpy of reaction over R, and then multiplied by the difference between 1 over T2 and 1 over T1. So we have this equation for chemical reactions. And for physical changes, we can use exactly same equation. It's just we need to treat those physical changes as if they were chemical reactions. So we're going to treat the vaporization as if they were chemical reactions. We go from liquid water with mole fraction X to water vapor at 1 bar. And then we can replace T2 and T1 with T-vape2, T-vape1 for vaporization. And over here, this is replaced by VAP as well. It's no longer a reaction, it's vaporization. We're just changing the notations. And what about the equilibrium constants? Again, we treat this as if it were a chemical reaction. So it's going to be product on top, which is just 1, the standard state. So you have this 1 bar over P naught, which is just 1. On the bottom, we have the reactant with a mole fraction of X. So the standard state for this liquid water is when it's pure, when X is 1. Now what if we added some solute? Now we just use X. X denotes the mole fraction of water in the aqueous solution. So K has such an expression, and we now can replace this K with 1 over X. And this K sub 1 is just 1 over X under condition 1. So we can do that. For convenience, we usually pick a standard state. So what if we have pure water? When we have pure water, X is 1, right? Pure water, X is 1, so K is 1. Alright, so we have pure water as the standard state. And now we have the vaporization temperature of pure water. Okay, over here, the common name is actually the boiling point of water under 1 bar pressure. Alright, I think it's very close to 100 degrees Celsius. Under 1 bar pressure, the boiling point of pure water is 99.6 degrees Celsius. So again, we're replacing this K with just 1 over here. So we're talking about pure liquid water, so that's why it's 1 over 1. And over here, this is just the boiling point of pure water under 1 bar condition. So now we have this equation because this part is simply 0 and this part is negative Ln(x). So from here to here, it's actually simple algebra. On the left hand side, you have negative Ln(x) and then multiplied by negative R and then divided by delta H of vaporization. You have this term. And this term is 1 over the boiling point minus 1 over the boiling point of pure water. This is the boiling point of water in an aqueous solution. And this is pure water. So we have this equation. Now let's look at this equation and do some semi-quantitative analysis. So when x decreases, alright, this whole thing decreases. Alright, this whole thing decreases. That means this decreases. And when this decreases, that means the boiling point of water increases. So somehow if you have a lower fraction, mole fraction of water, you have a higher boiling point. That's why when you add antifreeze in water, you lower the mole fraction of water, you increase the boiling point of water. In general, adding a solute in water increases the boiling point of water. And by how much? Just plug in those values here. You have the enthalpy of vaporization of water, you have R, you have the boiling point of pure water, and then plug in all the numbers, and then plug in X. You will get the boiling point of water in the solution. We can also analyze the fusion of water similarly. Again, we write out the fusion process as if it were a chemical reaction. From ice to liquid water with a mole fraction of X. So on the right hand side it's a solution. On the left hand side it's pure ice. Well, it's just because if you cool an aqueous solution, usually water freezes out by itself and you get a perfect crystalline structure of water, and that's pure ice. Now we write out this equation and we will analyze the expression of the equilibrium constant. That's the product over the reactant. Now we have water, liquid water on the right hand side with a mole fraction of X. That's the product. So K is X divided by 1. Because we have ice here, it's pure solid ice, therefore we use 1 here as its standard state. Now we replace X, all the K's with X, because K equals X for the fusion. Then we have this equation. And now we kind of just move things around. We multiply both sides by R. We divide both sides by delta H of fusion and move things around. We can go from here to here. This is just algebra. I'll let you verify this yourself. And now let's analyze this equation semi-quantitatively. What if we add antifreeze in water? What will happen? Well, when you do that, X decreases. Alright, X decreases. And then ln X decreases. And therefore this term decreases. And we're minusing this decreasing term. That means 1 over T fusion increases. When 1 over T fusion increases, that means T fusion decreases. And T subfusion is simply the melting point. The melting point of water in a solution is lower than the melting point of pure water. So in summary, when you add any solute into water, it increases the entropy of water and therefore lower its chemical potential. You have liquid water now stabilized. The liquid phase of water again is stabilized. That means you have a wider temperature range for the liquid phase, and that means you need to widen the temperature range for the liquid phase. And now you have melting point depression and boiling point elevation at the same time. Now we have learned actually 4 different colligative properties. The first is the Raoult's law. The partial pressure of species I on top of a solution is equal to the mole fraction of this species in the solution multiplied by the vapor pressure of pure I. That's number 1. It only depends on the identity of the solute. It does not depend on the identity of the solid, only quantity. I'm sorry, osmotic. No, the partial pressure of the solvent only depends on the quantity, but not identity of the solute in an ideal aqueous solution. And also we learned osmosis phenomenon, and now the melting point depression and boiling point elevation. So when we add a solute into water, we may observe all these four colligative properties. Again, the equation for melting point depression is this. It looks a little complicated. For general chemistry students, they usually learn the melting point depression is proportional to the mole fraction of the solute, something like that. So let's derive that equation. So first we have this equation, but when x is very close to 1, that means mostly it's still water. Lx is close to x minus 1. X minus 1 is negative x of solute. And now we can replace negative Lx with x solute. Now we have this equation. And once we have this equation, we can take the reciprocal of both sides. So we get this equation, and then over here. And now I just want to talk about mathematics a little bit. The reciprocal of 1 plus delta is 1 minus delta, approximately. Alright, so what I'm saying is, over here, when you see 1 plus a small number on the bottom in a fraction, so 1 over 1 plus this delta, I'm going to call this delta. 1 over 1 plus delta is approximately 1 minus delta. So we have this equation. Now we have the fusion point or melting point of the solvent. It's equal to the melting point of this pure solvent multiplied by this. And you can see this is less than 1. And that's why we call this melting point depression. And over here you have R on top over here, and then X of solute on top, and then you have actually T fusion over the enthalpy of fusion. What is that? Actually, it's entropy of fusion. So right here. So if you are given a substance, you can actually change its melting point by simply adding another chemical into this substance. And over here, you're looking at the relative change of the melting point. The relative change of the melting point is negative R times the mole fraction of the solute, the foreign substance, divided by the standard entropy of fusion of the solvent. Again, the relative change is approximately this. So this is proportional to X solute. And if you have, for example, some information about the identity of the solvent and solutes and the mass of solute and solvent, I think you can compute this X solute easily. Alright, so we can see the relative change of the melting point is negative, and we can plug in numbers here to get the relative change for the melting point. For the boiling point, we can also derive its relative change just similarly, and it's approximately this. If you compare these two expressions, we have a negative sign here and no sign here. Why? This is melting point depression. This is boiling point elevation. And another reason, more fundamental reason, is when you look at the vaporization of water, this ideal solution of water appears on the left hand side. So the equilibrium constant is 1 over x. But if you're looking at fusion, the ideal solution is on the right hand side. Alright? And it's going from ice to liquid water, so the equilibrium constant is x over 1. For melting. For boiling, it's 1 over x. So that's why you have a negative sign here, no sign here, and that's why it's melting point depression and boiling point elevation. However, other than that, these two look similar except on the bottom. The entropy of fusion should be replaced with entropy of vaporization. Chilton actually studied the entropy of vaporization for many liquids. It's usually around 90 joule per mole Kelvin. So you can plug in 90 here, you can plug in R there, and roughly the relative change of the boiling point is then X of solute over 11. And therefore, if the mole fraction of the solute is 0.11, you do this division, 0.11 over 11, the boiling point in Kelvin increases by 1%. Now let's look at a numerical example 8.2.2. Let's compute the melting point and boiling point of an ideal solution, an ideal aqueous solution that contains 0.1 mole antifreeze and 0.9 moles of water. So first, we know the mole fraction of water is 0.9. The enthalpy of fusion and the enthalpy of vaporization are both given. First, let's look at fusion. So we write out this equation. We plug in x equals 0.9. We have negative enthalpy of fusion on top, R on the bottom. Make sure you convert the kilojoule to joule, and we have this equation. I used Wolfram alpha to calculate the melting point. It's 263 Kelvin or negative 10 degrees Celsius. So by adding 0.1 antifreeze to 0.9 mole water, you lower the melting point by 10 degrees Celsius. We do similar things to the boiling point elevation analysis. Over here, we plug in x equals 0.9 on the left hand side. On the right hand side, we're plugging the enthalpy of vaporization over R. This is just the boiling point of pure water. We use Wolfram alpha to do the calculation. We get 103, so it's 3 degrees higher boiling point elevation. Or remember, in the previous slide, we had this calculation over here. Approximately, the relative change of the boiling point is the mole fraction of solute over 11. So if we have the mole fraction of the solute, which is 0.1, we plug in 0.1 here over 11, and then we compute this. We also get roughly 376 Kelvin, so these two match approximately. This is supposed to be more accurate on top. This is less accurate because this is an approximation. We actually used the Taylor expansion of the natural logarithm of the mole fraction of water, and we used the truncated form of that Taylor expansion. Now let's look at the freezing point depression again. What if we mix two solids? For example, we can mix gold and silicon. When we mix gold and silicon, we actually lowered the mole fraction of both. Alright, now if you look at this phase diagram, we have temperature here in Kelvin. We have the mole fraction of silicon here. How do we read it? Over here we have 100% silicon with a melting point of 1687 Kelvin. On the left hand side we have pure gold, okay, 0% silicon, all gold. The melting point is 1337 Kelvin. Now over here we have the liquid phase. We have a solution made of gold and silicon. So let's look at gold first. 100% gold. But if somehow we add a little bit more silicon into this liquid gold, it's going to lower its melting point. The more silicon we add into gold, the more we can lower its melting point. How low? All the way lower than 600 Kelvin. So we can lower the melting point of gold from 1300 Kelvin to only 500 Kelvin ish. Similarly, we can lower the melting point of silicon from 1600 Kelvin also to around 500 Kelvin. So the melting point decrease is showing for gold here, for silicon here. At this point, actually both gold and silicon have the same melting point, which is 536 Kelvin. You need a certain composition. I think you need roughly 0.186 as the mole fraction of silicon, and then 1 minus 0.186 as the mole fraction of gold. And again, we can compute this melting point for both gold and silicon. At this temperature, we have again gold and silicon with the same melting point. So what I'm going to do is, first I'm going to name this melting point eutectic point. So now we have 1 over the eutectic point is equal to 1 over the melting point of pure A. Okay, this is the melting point of pure A. T sub m stands for melting point. And we have pure A, and then minus this correction that involves the mole fraction of A. And 1 over the eutectic point is the melting point, 1 over the melting point of pure B, also minus this part. We have XB on top, the enthalpy of fusion on the bottom. So again, over here, this gives you the melting point of A in a solution. This gives you the melting point B in a solution. And now we have A and B in the same solution. So it's possible for the melting point of A and B to be the same. We call that eutectic point. But we need to solve this equation to predict the eutectic point. Alright, so now let's look at the phase diagram again. What if you start with 50% gold, 50% silicon? These two numbers are mole fractions, half-half. Let's say 1 mole gold, 1 mole silicon. And then we start from here, 50. Alright, we go down. So at 1600 Kelvin, you have only a liquid. When you hit this temperature is a little below 1300. Let's say this is roughly 1260. What will happen? What happens is we're hitting the melting point of silicon at this point. So silicon, pure silicon, starts to precipitate out of the solution. So you get 100% silicon. And once you have 100% silicon precipitate out of the solution, you have lower mole fraction of silicon in the solution. And you have higher mole fraction for gold. Because gold stays in the solution, part of the silicon leaves the liquid phase. That's why this mole fraction will drop, for example, from here to here. And here you have even lower melting point of silicon. It's 1200. So you have more silicon precipitate out of the solution. Alright, keep doing this. You keep lowering this temperature. More and more silicon precipitates out, and you have lower and lower mole fraction of silicon until you reach here. At this point, you have 18.6% silicon, and you have 81.4% gold in mole fractions. At this point, both silicon and gold have the same melting point, 536 Kelvin, and then both should solidify at this temperature. So at first you get a lot of pure silicon solid until you reach this point. At this point, you will get solid gold and solid silicon at the same time. Alright. There's some numerical example, so you can always look at the phase diagram. In this case, it's temperature versus mole fraction phase diagram. You have two components. You have gold, you have silicon. Pure silicon has a melting point of 1687 Kelvin. Gold has a melting point of 1337 Kelvin. But again, if you mix them with the right composition, you can lower both melting point of gold and silicon to only 536 Kelvin over here. So that's a big decrease of melting points for both chemicals. And now we have one data point over here. We know pure silicon has this melting point. And then let's look for another data point. Let's look at this line, 1600 Kelvin. It crosses here. The mole fraction is about 0.83, I think. So this is 0.8, this is 0.9. So we have a second data point. So when I have two data points, I can use this equation to compute the enthalpy of fusion for silicon. So on the left hand side, I have Ln(x) minus Ln(1). 1 is the mole fraction of pure silicon. X is the mole fraction here, 0.83. Now the right hand side, negative enthalpy of fusion for R, we know what R is, and then 1 over T fusion, which is over here, 1600 Kelvin. And then the pure silicon melting point, 1687. So you can see we have this equation set up already. R, we know its value. We can just compute the enthalpy of fusion. After we compute this, we'll get 48 kilojoule per mole as the enthalpy of fusion for silicon. The literature value is 50, so pretty close. I mean, almost too close, because I don't think the solution made of gold and silicon is really an ideal solution. The silicon-silicon interaction versus the gold-gold interaction versus gold-silicon interaction, I'm guessing the three can be quite different. They can be quite different. So between gold and gold, it's like a metallic bond. Between silicon-silicon, it's more like covalent bond. I think the silicon-silicon bond is is a little stronger than the gold-gold bond, I believe. So I need to look it up. But I think a silicon-silicon bond is stronger than a gold-gold bond. But anyways, we can still somehow just plug in numbers and get a fairly reasonable prediction here for the enthalpy of fusion of pure silicon. You can actually compute the enthalpy of fusion for gold. How do you do that? You have one data point here, right? And then you select another data point along this curve, just another data point. I would select this data point because it's easy to see. We have 1200 Kelvin and the mole fraction is about 0.07 for silicon, right? It's 0.07 for silicon, so it's 0.93 for gold. So why don't you just use a mole fraction of 0.93 and a melting point 1200 Kelvin for gold, and also this number for pure gold, and plug in the equation. You can compute the enthalpy of fusion for gold as well.